Quantum computers could be the key to cracking one of mathematics' longest-standing puzzles. A breakthrough that might change how we understand symmetry and complexity across physics, engineering, and beyond. But here's where it gets controversial. While classical supercomputers have struggled for decades, a new study shows quantum machines can take on these challenges with remarkable ease, suggesting they hold real, practical power today, rather than just in some distant future. Los Alamos National Laboratory scientist Martín Larocca, teamed with IBM researcher Vojtěch Havlíček, has demonstrated that quantum computers can successfully factorize group representations, an advanced mathematical tool used to describe symmetrical structures in diverse fields such as particle physics, engineering designs, and information theory. Group representations are collections of matrices that represent the abstract concept of a group, which captures all ways objects can be rearranged or transformed. The challenge for quantum computing right now is pretty clear, Larocca explains. We need to identify what problems quantum computers can solve better than classical ones. So we focused on a class of problems that are known to be intractable for current classical algorithms. This is the essence of quantum advantage, the ability of quantum devices to outperform traditional computers on specific tasks. Their findings, recently published in the prestigious journal Physical Review Letters, reveal that quantum algorithms can break down group representations into their fundamental components, called irreducible representations. Much like how any number can be factored into prime numbers, these irreducible representations are the smallest building blocks of the symmetry described by the group representation. But unlike ordinary numbers, factoring these mathematical structures is astronomically difficult for even the fastest classical supercomputers. Especially when determining multiplicity numbers, the count of how many times each irreducible piece appears. Larocca and Havlíček tackled this problem using quantum Fourier transforms, a type of quantum circuit that performs transformations related to symmetry and patterns, including the well-known discrete Fourier transform used in signal processing. By applying these quantum techniques, they successfully factored several important loop representations that are central to real-world scientific applications. Why does this matter? In particle physics, for example, researchers rely on factoring group representations to precisely calibrate detectors by understanding how particles might spin or interact. Similarly, error-correcting codes, vital for reliable data transmission and storage, are designed based on these concepts. Even the cutting-edge field of advanced material science depends on such mathematical tools to predict and create new materials. Peter Shor famously showed that quantum computers can factor integers, cracking problems classical computers find extremely hard, Larocca adds. Our work shows that quantum computers can also factor symmetries, opening new doors for both mathematics and applied sciences. This dual race in quantum computing, developing powerful hardware and identifying problems where quantum machines outperform classical ones, is just beginning to bear fruit. Larocca's research not only confirms the potential of quantum advantage, but also highlights the strategic importance for nations to invest heavily in quantum technologies to remain at the forefront of this emerging field. Of course, this raises intriguing questions. Could this approach redefine limits in computational math? Will classical supercomputers ever catch up? Or is the quantum edge truly unassailable? And importantly, are we prepared to harness these discoveries responsibly as technology advances? This groundbreaking study was supported by the Center for Nonlinear Studies at Los Alamos National Laboratory and the Laboratory-Directed Research and Development Program. For those interested in the technical details, the paper titled Quantum Algorithms for Representation Theoretic Multiplicities is available in Physical Review Letters. What's your take? Do you believe quantum computers will soon dominate problem-solving in fields like physics and engineering? Or should we be cautious about declaring victory over classical methods? Share your thoughts and join the conversation.